Okay, well, welcome everybody. I'm glad that you came today. I realize it's the end of the semester. It's a difficult time for people, but we appreciate you showing up. It's the first meeting of December for the IMAG MSM Multiscale Modeling Group on viral pandemics. And today we have a single speaker from Texas who's going to be talking about GPU accelerated computing. And we look forward to that. As always, I need to remind you that the meeting is live streamed and recorded and made available afterwards. So we always have the slide of myself, Tom Helikar, who's traveling today, Jim Sluka, Lorenzo, and Joel to try to help things out. We have our communication channels. Please help us use them, especially the YouTube archive. If people aren't able to watch in real time, you have the opportunity to watch everything later on. There are a lot of great talks, many of which deserve to be seen by more people than watched them originally. And we have our Twitter feed, which people can use to try to help us promote things a little bit. Next week is the closing meeting of the year. We're going to have a discussion and review of where we are and where we've been, where we'd like to go. We would love to get your input. The slide deck can be shared. If people would like to have access to the slide deck, let me know. We'll make that available to people. There was also an email that was sent out asking for final comments and suggestions from people. We'd love to hear what collaborations developed through the working group, what grants you've gotten, if any, through the working group, what you'd like to see in the future from the working group, and also, of course, suggestions for speakers, papers that came out of the working group, and so on. So please do help us out by filling out those forms, and feel free to join next week and let us know what worked, what didn't work, what we should do differently. Announcements. We have a digital twin subgroup meeting tomorrow at 11 a.m. If you weren't invited, you need to be. Let us know. Reinhardt, I'm always happy to send an invitation for that. CJ's here to talk for himself, but there was an email from PJ Segal, who just joined the faculty at University of Florida, that he's recruiting a postdoc in computational biology. And he would love to hear from your students or your students' students. PJ, do you want to say anything about the position since you're on the call?
Yeah, absolutely. Thank you, James. And hi, everyone. So looking for a postdoc to work computational modeling, particular interest in epithelial dynamics, especially lung epithelial dynamics, usually in the context of respiratory disease and the immune response. Interested in modeling projects, everything from subcellular state dynamics all the way up to multicellular systems modeling. So my email's there on the slide. So it'd be great to see someone come in and get started as soon as possible. Thank you, James.
And I would send that announcement also to Lorenzo, and he can send it around to the whole email list.
Great. Thank you, James.
Any other announcements today? Okay. So we don't have anything scheduled for December 15th. My feeling is people probably would like to have some holiday, but if people would like a seminar on December 15th, somebody wants to volunteer, we can certainly put that on the calendar. So let me know. We're going to try reducing the frequency of the seminars a little bit in the coming year to see if that helps with attendance. I think people are maybe a little bit burned out by the pace we've been keeping for the past 2 years now. We have our first scheduled seminar January 19th on the Human Immunome Project, and then February 2nd, we have another seminar scheduled. Please help us by suggesting speakers. As always, suggest yourselves, suggest your postdocs and students, suggest the people who've written papers that you'd like to hear about, and we'll do our best to get them on the books. So without more delay, I'm going to turn this over to Baylor, who's going to be talking about GPU accelerated agent-based modeling in virology. And we're very pleased that you're willing to talk to us today.
Yes, thank you. Let me get these, let me share these slides. Is everybody able to see that? Fantastic.
Looks good.
Thank you so much. Yes, so thank you all for giving me this opportunity to come and talk about some of my work. I titled this presentation, Your Computer May Be More Powerful Than You Know, because today I'm going to be talking about a piece of hardware that is in a lot of computers these days that most people aren't aware of. And the way I'd like to go about doing that is by presenting an example. And this example is a model that simulates viral infections of influenza on a monolayer of 1 million cells. So I'm doing Plaque assay experiments of influenza infections. And in this example, we're speeding up these simulations by utilizing the hardware called GPUs, or graphical processing units. So this has become a term that most people are familiar with, especially if you're a video gamer or something like that, where the GPUs operate as something that can really make your graphics nice and things like that on the computer, or if you need multiple monitors and things like that. But we can repurpose that in order to increase our computational speed for modeling purposes. And I'm specifically going to be talking about how these GPUs can accelerate agent-based models today. Now, I want to take a moment and sort of point out how much I like this project, because I really feel like it takes biology, mathematics, computer science, and it really shows how those overlap, and how when you do interdisciplinary work, you can take a little bit from each field and approach a project in a new way and get really great results. So first, let's take a step and let's talk about agent-based models. Now, this is something that probably most of y'all are familiar with, but just to make sure we're all on the same playing field, an agent-based model takes a system and breaks it down into either naturally discrete units or into just smaller units of that system. And so an example here is, let's we say we have a tank full of fish, where we could represent this system with the agent-based model by modeling each in one of those individual fish. So we could model the fish, and the fish could be swimming around, and it could, once it would get close to another fish, it might eat that fish, or maybe when two fish get close together, it might produce another fish. But all those fish, we'll be modeling all those fish, and those fish would follow the same set of rules. Another example is, let's say we had a piece of metal, and we wanted to see how heat would diffuse across that piece of metal. Now here, we couldn't model each of the individual atoms, but instead we could just model smaller pieces of that piece of metal. And since we know how the dynamics of the heat diffusing on that little piece of metal would act, we could then model the larger piece of metal and watch the heat diffuse across that entire sheet of metal with different initial conditions. So why would we want to pick an ABM to model something in virology? Well, if we look back at that fish example, so in the fish example, we're modeling each of those fish. So we know the spatial relation in between each of those fish that's swimming around in that tank. Well, the reason agent-based models were originally employed was to include that spatiality of these viral infections. So inside of this culture dish that we have on the right, we would want to model all the cells that are in it. So then that we would know the spatial relation between one of those cells and all the other cells that are inside of it to try to capture those spatial dynamics. So this is something that's been done before. And here is some examples of some prior research that have included or used ABMs to include that spatial component. And one thing I want to point out about these different works is that when they modeled cells with their models had a fewer number of cells than what their data had, than the target cells that was in their data. And of all of these four different examples, there's a minimum of an order of magnitude, or there's at least an order of magnitude less in the number of cells that they were modeling and the number of target cells that they had in their data. Now, the reason I picked these four examples is because at some point in their paper, they talked about how computationally, the reason that they modeled a fewer number of cells is so that they could simulate, perform more simulations in order to do the statistical tests and the things that they needed to make their paper the way they would like it. And so this whole presentation and the paper that I was able to publish earlier this year is all about how now we have the computer resources to simulate millions or more cells that would match closely to what would be done in an experiment. So now we can talk about how we speed up these simulations. And now this brings us back to the graphical process units, or those GPUs I mentioned earlier. So a GPU is just a piece of hardware that has a lot of processors on it. So here's an example of the GPU that I use in my computer. And then here's an example of the CPU that I use in my computer. So like I said, the GPU has a lot of processors on it, and the GPU I have, it has 6,144 different processors on it. Whereas with the CPU, it only has 4 processors on it. Now, some of y'all who are familiar with computer hardware and things like that, you would know that a CPU has a much higher clock speed, or therefore each individual processor is faster than the GPU processors. You can see here that the processor on a CPU, on this CPU, is 3.6 gigahertz, where each individual processor on the graphics card is only 0.735 gigahertz. But if we are able to use all of those different processors that are on these different units, then we can manage to get way more computation power out of the GPU. And so a way of measuring this is something called a flop, or a floating point operation, and they normally do that per second, so it's flops. And so you can see here that on the CPU, it can put out 442 gigaflops, where the GPU can put out 19.2 teraflops. And so this means that the GPU is close to 10,000 times faster than the CPU. Well, now, like I said earlier, this is if you're able to use all of those processing units. And on the CPU, typically, when you compile a code on it, that CPU, it only uses one of those units to compute that code. So the CPU puts it onto one processing unit, and then that processing unit goes to the first line of the code, then to the second line of the code, the third line of the code, and then the fourth line of the code. And so this is what's called it being done serially. Whereas with the GPUs were designed to do all that graphics processing and to manage all the different pixels on your screen. So they have a natural way of talking to each one of those processors across the GPU in a way that you can, if you write it properly, you can split your code across all the different processors on your GPU. And then each one of those processors will crank through the steps in your code, and you're able to do many more processes at the same time than when compared to the CPU. So here, the GPU and the CPU, it's not something that you just like replace the CPU with the GPU. They work in tandem. So the CPU, you put your code on it, and then you tell the CPU to send your memory that you want to work on and the code over to the GPU. And then the GPU will set up that code or that memory in its own memory and then start to process through that code. And then it can report back to the CPU as you tell it to. And then it can sit for a while crunching away on your problem and then report back again. And then you can just keep doing that until you set up something in your code to tell it to stop processing. And so this allows for the CPU or for the GPU to just be sort of like a computational tool to just increase your computational power on your computer. So now that I've sort of walked through what a GPU is and how it's sort of used in these codes, I want to show you the example of the simulations that I've done. And so here, just to remind you, I'm doing Plaque assays where I'm modeling 1 million cells that are inside of a culture dish. And I represent the uninfected cells as green. And so that would be, if you were to be looking at this Plaque assay up here, it'd be as if it's the white all out in the middle is represented as green. And then the uninfected cells that haven't begun to produce virus, or the eclipse cells, are colored in cyan. And then the infected cells that are beginning to produce virus are colored in red. And then the dead cells are colored in black. And then over the top of this virus, which is normally not, or normally the top of these cells, which is normally not seen, is the virus. But you'll see that and it'll be colored in purple here in a little bit. So next, I want to show you all some the real-time simulations, or sorry, some videos of the simulations. So here, like I said, on the left, we have a culture dish filled with all uninfected cells. And then on the right, we have the virus that would be diffusing over the top of those cells. And so what's going to be happening in this video is I'm going to randomly choose some cells to be in the eclipse state. And then once those begin to start producing virus, you'll see on the right that virus diffusing across the dish. So here I'm going to begin the video. Okay, so it's running a little slow, I think because of Zoom, but what you can see here is where those initially infected cells, once they begin to produce that virus, you can see the virus pop up on the right. And then as that virus diffuses across the top of those cells, you can see the infection front spread along with that virus. And I find these videos really satisfying. I think they're just super cool to watch as all the cells in the dish become infected and they all go to dead. Something's very satisfying about it. I used to always joke with a friend of mine that when you do GPU work, you always end up making the best screensavers and things like that. So this next slide, I want to show you a zoomed in section of that Plaque assay, so you can really see that infection spread. And so here's that zoomed in section, and in the very middle, you'll see one of the infected cells here in a moment, and then you'll see the virus diffusing on the right. And so here, I really like the zoomed in photo because you can see each of the individual cells if you look closely. And then you can see as the cells transition through each different stages of infection, that it's a stochastic process and you see all the different things happening. So now I've shown you that the videos of the simulations, it's neat that, you know, there's real experimental data, and with these agent-based models, we can produce simulations that qualitatively look like what would be going on in a real experiment. But earlier, what I was talking all about was speed and speed increases. And so in this next slide, here is the same code, but I've written it in 3 different programming languages. So in green at the top, we have, it's written in Python, and then in blue is written in just C alone. And then in orange, it's written in C and then plus CUDA in order to utilize the GPUs. And you can see that when you start utilizing those GPUs, the code is much quicker when it's simulating the cells. And so if we look at the far right over here, where where each of these different codes is simulating 1 million cells, the Python code, it's close to 10 to the 5 number of seconds. So here I was simulating 1 hour of simulation time, how long it would take to simulate 1 hour. And here it's close to 10 to the 5 seconds. And so that's a little over a day worth of time to just simulate 1 hour. We're down here with the GPU code, or the CUDA code, utilizing the GPUs, you can see it's close to a second for 1 hour. And so that means that the CUDA code is 70,000 times faster than the Python code. So now that we have these simulations, and we would like to compare them, to real observations. So I already showed you the qualitative aspect, but we kind of want to make sure that we can get some qualitative comparisons as well. So here's some real experimental data that was pulling from Plaque assays. And whenever we go to fit the model to this data, I used I did a sum of the squared residuals minimize on it. And then here's the result from that fitting process. So here in green is that same data. So that's the real experimental data. And then the dark blue line is the median curve of 10 different runs that I did in order to get a single fit for the parameter optimization. So each one of those 10 runs is in the light blue that you'll see in the background. Now, what's really neat about, since we're able to simulate these models much quicker, I can use these standard fitting practices. So I had my code run as a function, and I was ordered to call it from the SciPy minimize, or I was able to call it within Python in order to use it in the SciPy minimize function in order to do this, to make it do it for me. So, whenever you minimize with SciPy, it'll run through hundreds of parameter spaces. I think mine it would hop around anywhere from 300 to 500 different parameters before settling on which one that was the best fit that it determined. And if these simulations weren't able to run very quickly, then that would just be a non-feasible. But since they run so fast, I would be able to set one off in the morning, and then it was normally around lunchtime, I would be able to have a result. And so that just makes it really neat that just by simply having these faster simulations, we can lean back on some of those older, already established practices for fitting these models to data. And then here is just an example of those parameters that I pulled that was generated from fitting that data. And so next that's the model and how, I'm going to use it for fitting data and all those things. But for a moment, I want to look forward and kind of talk about a potential usage of this. And so in order to talk about how maybe we could use this in different computers and maybe get these assays into hospitals or into a doctor's office in order to generate these simulations in real time, let's talk about the memory that is needed to run one of these models. So the model I just showed you, it currently uses around 34 megabytes per million cells. And it's a fairly simplistic model, and it could have some attributes that would need to be added to it. So, of these different attributes we could add maybe syncytial formation, depending on which virus you were talking about. And if we would need to use floats in order to represent that. So we need to add 1 million different floats. So that would be about 8, or an array of 8, 1 million floats, that'd be about 8 megabytes. And then maybe we need to add the immune response. We need to represent that with floats. So that'd be an additional 8 megabytes. And then maybe we need to increase the heterogeneity of the different cells further. And we can represent that with something that takes up a little less space, but it'll still take an additional 4 megabytes. So altogether, this new model would take about 54 megabytes per million cells. Now, let's think even further down the line, and we need a more complex model. So let's just say that we would need a model that needed 100 megabytes per million cells. So there's a lot of different commercially available GPUs these days. So here, this is the Quadro P400. This is probably the least powerful GPU that NVIDIA specifically sells. And this is used if someone in a commercial setting would need to run a bunch of different monitors. I think it has 4 or 6 different plugs on the back for usage. And so these are fairly custom or very normal place in things like hospitals or different commercial settings. Well, with its 2 gigabytes of memory on it alone, we could fit into the memory of that card 20 different plaque assays of 1 million cells. And so similarly, if we bumped up the GPU to a Quadro P4000, which this is a GPU that I actually have, and it would be more if you were needed to run some sort of software that would also need to utilize an acceleration or something like that. It has 8 gigabytes of memory, and so therefore we'd be able to fit 81 different culture dishes of 1 million cells in it. And then if we bump up one more time to another GPU, this is the Quadro RTX 8000, where this is something you would have in a server, or if in a hospital where they would need to do lots of different image processing, either for MRIs or CTs, things like that, where you would need a lot of different computational power. So in this card, it has 48 gigabytes of memory, and we'd be able to fit 491 different culture dishes into that memory alone. So the reason I'm pointing these out is that these are commercially available standard issue graphics cards that hospitals already have in their computers for different applications. So if we were to make more models like this, fine tune them, tweak them, and have them have the results be able to use as some sort of predictor for human symptoms of disease, things like that, then the hospitals would already have they already have currently the computational hardware in order to run these simulations. And already have enough hardware in order to run these simulations for that particular application. And so that was just some kind of speculating forward about if we were to make the right model, then when as technology advances forward, there's already going to be potentially the resources out there to make this thing achievable. And so to talk about some more direct uses for this research, with increased power, you can run through a larger parameter space. So this is a project that I'm currently working on where it has, I have a 50-50 grid, and then I'm simulating 10 runs per grid space. And then I'm running it over a bunch of different parameters. And so for this figure alone, I have to do 25,000 different simulations. And so it takes about 4 days to generate just one of these plots, but where normally that would take way longer. But now with these faster simulations, I can investigate these very large parameter spaces. So that's one thing that's kind of really neat to come from this research. And then the other thing is that I'm able to do very specific hypothesis testing very quickly. And so lately I've been looking a lot at the ODEs that are used to model viral infections. And I've been wondering how they're connected to these agent-based models. And because I'm able to do this very quick hypothesis testing and generate a bunch of different simulations, it's actually given me enough information to write a grant that I applied to the Mathematical Science Postdoctoral Research Fellowship via part of the NSF in order I was able to apply to that, and it was all because I was able to do this testing and come up with these ideas in a new time frame so that I could have the information in order to apply to that grant. And so that concludes my talk. In conclusion, I'd like to thank my advisor, Dr. Hannah, and then I'd also like to thank you all for giving me the opportunity to give this presentation. So thank you.
Okay, great. That was compact, interesting, and timely. Let's open the floor up to questions. I know I have quite a few, but I'll let other people maybe. Well, no, I'll start one. So you have two basic components to your model. You have a agent-based model for the cells, and you have a diffusion solver. What fraction of your computer time is used solving the diffusion equation, and what fraction is solved updating the agent states?
So the diffusion equation is discretized over the space of the cell.
Mhm.
So they're done in the same step. So it's equal parts. The only time where there's sort of a relief on the work is when you don't have to check. It's like when all the cells are dead, then you don't have to check which cells are alive anymore. So you can turn, you can have you can skip that section of the code and just do the diffusion over the top. But in terms of like having to run one simulation and then update the other, they run at the same time and update.
But you don't have an estimate of what fraction of the time is being used to do the averaging and diffusion versus a fraction of the time being used to do the state updating of the cell state.
Well, so are you talking about like?
With the diffusion average isn't that hard. You measure the concentration of your neighbors and you divide by 6 and you keep updating that way. I assume that's how you just do a direct diffusion solve.
It's almost like that, yes. And so let's say that takes 8 lines of code, then when you're doing cell-free infection, it takes about the same lines of code, so it would be probably roughly close to half, split 50-50.
So the other thing that typically shows up as an issue, which is not true of the diffusion step, well, it could be depending on how you do the diffusion step, but is not true of the diffusion step, but is true of the others, is that when you have stochastic choices, the cell measures the virus concentration and that has a probability of becoming infected or a probability per unit time of dying, then when you have those stochastic steps, typically it breaks the pipeline in your GPU, right? So because the conditional breaks the pipeline, and so it slows you down. I don't know.
The pipeline.
Well, normally the GPUs are anticipate calculations, so that the calculations are pipelined. And if you have a conditional, then that particular pipeline has to reset and restart. And so it runs a little bit slower, sometimes a lot, sometimes a little. If your main benefit is just that you have a lot of processors, that doesn't matter. Right. And so I'm trying to understand how much the stochasticity of the cell updating slows you down. Clearly not much. It runs very fast. But that's the other thing. That's the other reason I was trying to get a sense of the ratio, because the diffusion is deterministic. But the updating of the cell states is stochastic, at least in typical versions of the Plaque assay.
So I see what you're saying. The weighting that is involved. So there is a bit of weighting. So what that's called is you have to sync all the processors. So you come to a point where one of your processes can't move on. Can't move back up to the for loop that it's supposed to be doing because it's contingent on something that one of the other processors is doing until it finishes and gets back to the top. Then they all can't proceed forward. So if that's what you're talking about, then it's about 2/3 is done. That weighting increases that process time by about 2/3. So once you're done with that weighting and all the cells are dead, and you can know they're just going to be in one state because there's no regeneration in this model, the model just becomes crazy fast. And that statistic I told you, or that value I told you of 1 second for the computation time, that was actually for the beginning of the infection, where everything is being counted and all that stuff. And so in the latter half, the hours just fly by, and I'm pretty sure, if I remember correctly, it idles around about 1/3 of the computation time. So I hope that answers your question.
Well, that also gives you basically, because if all the cells are dead, the only thing you're doing is diffusion. So that tells you what
Yep.
fraction of your computation is diffusion. Okay, thank you very much. That was really fascinating. Other people, questions?
Hello, this is John. Hey, I'm just reading today that the lenders that loan Bitcoin mining groups huge amounts of money for very expensive, I assume, very fast processors are getting the processors delivered to them, because the processors were the collateral and the only collateral. And does that suggest there's going to be a big pile of useful processors for what you're doing if you knew which bank to go ask? I mean, they're talking about 85% loss in the value of what those were. Were they using the same kind of processors you're talking about, or is it a whole different world?
So
of no,
I'm not a Bitcoin person, and so I'm very far from a Bitcoin expert, but I can talk a little bit to what you're talking about. So the processors are not the same in the terms of what they're proprietary oftentimes when they're made. And so they're not like AMD brand or NVIDIA brand, where I'm very used to using NVIDIA brand because they have a very clean API called CUDA that you're able to interface with C directly to the GPU. But there are softwares that aren't as easy to use, but they're definitely achievable. I'll name a few. You could use OpenCL if it's a true written as a graphics processing unit, or there's different ways to compute across multiple different processing units. One is called OpenMP. There's OpenACC. Any of those different things, if you can learn how to use it, you do. So the big thing about those processing units is that you might not be able to use them because they might not interface well. They're probably very specialized, but the fall of Bitcoin and the Bitcoin using GPUs so heavily in their mining processes, it does mean that since Bitcoin's falling, the demand for GPUs is falling, so the price will go down. So now might be a good time to snag yourself a GPU, and you don't need that powerful of one. There's ones that are coming out that have 48 teraflops of processing power, and that's more than a supercomputer that most universities' supercomputers are able to do. And so you can have one card in your computer do all of that processing power. To kind of finalize, say again, now might be a good time to buy a graphics card if you're looking to get into this sort of thing.
NVIDIA stock has certainly tanked because of the crypto meltdown.
Yes, yeah. But they are, so I just went to the supercomputing conference that was hosted in Dallas, and it was fun. And normally NVIDIA is there, and this is the first time that they didn't make an appearance. They were a part of two other companies, but not their own standalone show. And everyone was talking about the cryptocurrency falling and stuff like that. But people that are into supercomputing and processing all that, that's it's not really what they're there for. So they didn't really care. NVIDIA stock dropping means the processing units are cheaper. They're selling you for a better price and things like that. So.
I've got a question.
Absolutely.
Well, first, thank you for the talk, Baylor. It's a cool topic and certainly relevant to a lot of the stuff that we work on. So I was wanting to know a little bit more about some of the computations that you've reported in your simulation and the corresponding performance metrics. So yeah, so you have some visualization that you've included from your results, and if I understood you correctly, those simulations, when you're doing GPU acceleration, you just have the data all on the card, doing everything there, and no scheduling back and forth between like the CPU and the GPU. Is that correct?
No, I do have a scheduling.
Okay.
So it reports back every simulated hour. And I chose that because of oftentimes the granularity of the experimental data. So,
Sure.
but I can, so the time step itself, just in case you're wondering, is 18 seconds.
Okay. Yeah, great. So, and so with that, with those sort of like, it's not quite synchronization, but with those like 1 hour intervals or whatnot, are you doing like data transfer back to the CPU, and that's when you're doing either visualization or storage for rendering later?
So yes. So I think in the videos that I showed you, I think I had it spit out every half hour, just to make a slightly smoother video. But so when I'm running a standard simulation, so the CPU copies everything over the GPU, and then the GPU will run for 1 simulated hour, do a copy back to the CPU. The CPU will then record it to file, I think I had to count all the cells and stuff and record it in a file as it goes, and then spit back, or then it'll so then there's no copy back.
Mhm.
The GPU can just continue going right after it's done copying, and the CPU can copy stuff on its own, or the CPU can write things to file on its own, since they're in 2 different spaces.
Yeah.
Does that
Okay.
answer that question?
Yeah. Well, and so the reason I ask is, for some simulation platforms, like those that some of us develop, there's support for like real-time visualization, where those synchronizations in data, to be able to pull the data from the card and do something like real-time visualization, those events happen much more frequently. Something not quite like 60 frames per second, but something that's up to a refresh rate, to where like a data could be browsed interactively. And so I was wanting to know if you could speak to like the impact of that sort of like those aspects of the heterogeneous architectures, and what sort of cost you could maybe expect with doing like much more synchronization with respect to the performance metrics that you reported here.
Right. So I don't remember how much the memory copy is surprisingly most of the time sink. So it takes a very long amount of time to copy the memory back. So you're 100% accurate saying that it'll increase the cost, but I don't remember. I don't remember how much it is here. Oof. So if you were trying to do like visualization in real time, there are some workarounds that you could do that you wouldn't have to copy back to the CPU. There are ways of just having it output via the GPU to the screen. That's a beast all on its own to handle. Their OpenGL coding and calling into there's a new thing called Vulkan that kind of allows that to be a little quicker, but it's very, very difficult to handle. So you can have the GPU do all your drawing and stuff for you for your visualization. So that is one way to work around that. But in terms of specifically for this code, I don't know those things off the top of my head. I could run for NVIDIA's software, there's something called I think it's the NVIDIA visualization profiler that it comes standard when you install NVIDIA drivers and things like that you can open up your code in, and it'll show you each of the individual parts of your CUDA code that are taking up the memory and how much time or how much memory they're taking up and how much time they take to run a process. So you could easily profile it from there. But in terms of my stuff, I would, if I were to spit out every time frame, I think it slows it down at least by a half, if not more. Because I was doing some testing the other day and I had to spit out every time step, and it's dramatically slower, but it doesn't make it, it's surprisingly much faster than I think it would be. So if that answers your question.
Yeah, well, and if I can take up 2 more minutes, James, is that okay? Great. So the reason I ask is because, typically, like GPU accelerated code is not written like de novo for a project. Typically, software developers will port their code based on like an existing implementation. Usually GPU acceleration, I wouldn't say usually, very often GPU acceleration is a feature that will be added to an existing software package. Which is I recognize is pretty contrary to what you've discussed here.
Yes.
Yeah. And so I was just trying to understand what you reported here today, sort of in the context of what role these features and capabilities play in improving existing software or software that say supports machines that either do or do not have GPUs available.
So okay, so to talk, I think there's 3 things to talk to there. I'll see if I can remember them all. Just so everyone else is aware, yeah. Oftentimes when people, when some sort of software company will mention like GPU acceleration available, that's using what I mentioned earlier called something called OpenMP, where it takes your code and somehow throws it across all these different processing units. Where here, this is more direct programming down to the individual processing level unit or unit level. And you're able to get much more speed increase doing it this way. And in my opinion, when I learned CUDA, I hadn't taken any programming courses yet. It was actually like what's it called, a baptism by fire of sorts. They are equally as difficult to learn. And so if you're wanting to do high performance computing, but you're wanting to do projects just on your own desktop and have immediate feedback, CUDA is a great resource for that. So that was the first thing. And then the other thing that kind of came back to memory is that the memory transfers that happen get faster and faster as you have better, more advanced technology and things like that. And you can definitely have real-time feedback because I didn't employ it with this model, with this code specifically, but for the prior research that I did that was in astronomy, we we definitely utilized, like zooming around and looking at the collisions of these stellar objects that we were looking at. And so if you're wanting to use it, I don't know if it's for a clinical purpose for like a client to look at this, or if it's for educational purposes. If you wanted to be able to show people like hands-on, like here's what, here's the system and it's happening. As technology increases, you could definitely do that probably in real time with these simulations. And if you were just wanting to use it as a teaching resource, you could bump down just one level, 500,000 cells, and get, a dramatic increase. It would just be much quicker and be able to visualize everything as quick and use that as a teaching resource. And then I thought there was something else I wanted to mention, but I can't remember it now.
Yeah, no worries.
Did that
Yeah,
help?
yeah. Oh yeah, yeah. I
Okay.
just yeah, thank you very much. I really appreciate it. And again, thank you for your talk.
Yeah, definitely.
Well, it's interesting that you found CUDA not that hard to learn. People
I've
often find the GPU algorithms challenging.
I've been I've been told I'm weird, so take that with the grain of salt that I say it's easy. But I think it's very once you get parallel processing, how to parallel process in here, I personally feel that when little c, CUDA is you're able to just write what you think in terms of math and get it done.
Well, certainly those execution times are amazing compared to, I mean, you say 70,000 times faster. I was just talking to TJ. I bet it would be even 100,000 times faster than running the same code in our simulation environment. But one thing that's interesting to me is that in the old, it's also just the GPUs have gotten better, because we actually had GPU accelerated code 10 or 15 years ago. And we wound up losing it because nobody used it. And if your users don't, then as the hardware evolves, even CUDA changes. And so it wound up not working anymore, and people didn't ask for it. So basically the GPU accelerators dropped out of the code base, largely because of what you said, which was that you gained an enormous amount of time in the GPU, but the copies back and forth to the CPU memory were so slow. And the way we set up our code, you had to do that so often that the acceleration wasn't that great. So people found it inconvenient. But when you do something like what you described, where you keep almost everything on the GPU and you stay within the memory limits of the GPU, then of course it's incredible. So to me, that's a great demonstration. We were thinking about trying to define good, sort of what is a good simulation model, biological model to use as a benchmark. And we've been thinking about a lot of things, but I would say, TJ, that actually we should run this version of this, his frozen cell version of on hex lattice, maybe, although some people don't have hex lattice, of exactly this model. We should look at exactly what your rules are and implement it in our software. It should be implemented in Physicell. It should be implemented in Biocellium. And use the Plaque assay as a demo, because you have diffusion, you have cell state change, you have stochasticity. You really do need a big assay. You really do need a lot of cells. And so I think that could be a great, try to get grouped together. Maybe you want to do that as a project. Crack the whip on everybody who has these multi-cell modeling frameworks and say, okay, it'll only take us an afternoon to implement it. We'd have to sit with you to make sure that we actually had exactly your algorithms. The rule for transitions is right. Poisson relations are right. But once we did that, I think everybody has all the pieces. And we could then really do some interesting benchmarking. I think that would, what do you think, TJ? Would that be fun?
It could certainly be interesting. from a methodological standpoint and also from a computational one.
Because there are very few models that have been formally replicated between modeling frameworks. There's the famous paper by the Chase group at Oxford that did it. But in general, people don't do that. And the Plaque assay is complicated enough that it's interesting and simple enough that it would be almost guaranteed to work on almost any modeling framework. And it's challenging enough in terms of computational burden that it's a good exercise.
Yeah, that sounds like a fun project.
So maybe send me an email if you like, and we can see about it.
Definitely.
We certainly have the Plaque assay simulations, but we'd have to adjust them to make sure that they really were the same as yours. So it's an apples to apples comparison. So for example, well, it doesn't matter. Any other questions before we break? Okay, well, thank you so much. That was great. And I will see people next week for our 2nd year anniversary. And I look forward to hearing from you, Baylor. That was great. Very inspirational talk. Appreciate it.